Hi everybody, I wanted to work question 12 on work session 17. So this is a titration problem. We have 25 milliliters of 0.125 molar pyridine and it's titrated with 0.1 molar hydrochloric acid. We want to calculate the pH at each of the volume of the added acid. So we're going to do it 0, 10, 20 milliliters, equivalence point, one half the equivalence point, 40, 50, and then sketch a titration curve. Alright, so first order of business, anytime you do a titration, you want to identify what's in your beaker and what is in your burette. And so, what's in our beaker is pyridine, C5H5N. And if you're taking my class and you have this molecule on your assessment, then I would give you the chemical formula. So you don't need to memorize it if you're taking my course right now. If you're taking organic chemistry onwards, then you would learn that molecule. And in our burette is hydrochloric acid. And just want to identify, well, what is hydrochloric acid? Well, it's a strong acid. What is pyridine? Strong acid, strong base, weak acid, or weak base? It's a weak base. So what we're working with here is a weak base, strong acid titration. It's always important to kind of recognize that. Now part A was asking us, what is the pH of the solution when 0 milliliters of HCl has been added? So what is it before we even start the titration? So, in my online lectures, I keep asking you, what's in my beaker? Well, at this point of the titration, when no hydrochloric acid is added, all we have is a weak base. If all we have is a weak base in solution, then we need a rice table. We haven't added any acids, so no need for a BOD table right now, no need to do any sort of stoichiometry, just do the rice table. So, with that, C5H5N, pyridine plus water gives us the conjugate acid. If pyridine is a base, it is a what? A proton acceptor. So the conjugate acid of pyridine looks like this, where it has an extra proton and then it went from a neutral to a positive formal charge. Water is acting as a base, and so therefore, as an acid, my apologies, it's acting as an acid, as a proton donor, and so we're left with the conjugate base of water, which is hydroxide. So make sure you're using those definitions to guide you into determining the correct products as you work through these types of problems. All right, so initially we were given that we have a 0.125 molar pyridine solution . And that, you just do a typical weak base rice table here, plus X, and then X and X. And because it's a weak base, we set it up to what? The KB expression. So KB is equal to products over reactants. And so this is equal to X squared over 0.125 minus X. The KB of pyridine, you could look up in the back of the textbook. It's 1.7 times 10 to the negative 9th. We're going to assume X is small enough to ignore, especially since KB is so small and we're working in relatively not so dilute concentrations. And so when you solve for X, you should get 1.4577 times 10 to the negative 5th always ask yourself, what does that mean? What is X? X in this case, if you've predicted the reaction correctly, is the hydroxide ion concentration. So this is equal to hydroxide. From there, you can find the POH, which is the negative log of the hydroxide ion concentration, so 4.8363, and then the pH is equal to 14 minus the POH, and so that is 9.16. So always ask yourself, what is X? And that's always based on your predicted products of your equation. So in this case here, we're dealing with a weak base. Hydroxide is the conjugate base of water, and so that's our X. So I had to use the POH to get to the pH. If you've been watching my online lectures, then you know I always like to justify the numbers we've calculated. So a 9.16 indicates a basic solution. If what's in your beaker is a weak base, we would expect a basic pH. And so that should give us a little bit of peace of mind that we set up the equation and the problem correctly. All right, the next step here was what happens when we've added 10 milliliters of HCl. Now, when you add this strong acid to this weak base, a reaction will occur. And when that happens, you need to use a Baugh table. So the Baugh table is a way for us to do some solution stoichiometry quickly. All right, so first order of business, we know that HCl dissociates in the presence of water into those hydronium ions and the chloride anions. Now, it's up to you whether or not you want to just write HCl plus pyridine and give the products of that reaction. I tend to, when I teach and when I work through problems, I use only the key ingredients. I leave out the spectator ions and give you more of the net ionic equation in a sense. So the equation or the reaction that takes place, we have C5H5 in pyridine, and then plus the hydronium ion. Like I said, if you want to write HCl there, that's fine. I tend, in my years of teaching, if the chloride's present, it tends to confuse students. So that's why I go straight to like the net ionic equation. All right, the hydronium ion, it's going to donate a proton. It's definitely acidic. So that pyridine's going to take that proton to make the conjugate acid. And the conjugate base of the hydronium ion, because it's donated a proton, is water. So please don't be overwhelmed with predicting products of these reactions. It's the same thing. You're just moving one proton at a time, and that is it. It's a Baugh table, though, and not equilibria, because we are actually running a reaction here. The arrow is going forward, right? We're not just doing equilibria here. All right, when you do a Baugh table, don't forget to work in moles. And so when we put in, we have 25 milliliters of a 0.125 molar pyridine solution. So from there, you have to figure out, well, how many moles is in my beaker initially before I add anything. And you would get 3.125 times 10 to the negative third moles. The hydronium ions, almost zero, so we'll just say 0. Conjugate acid is 0, and then we do not include water. Now, we have added some acid. We added 10 milliliters of a 0.1 molar acidic solution. So we've added in 1 times 10 to the negative third mole. So you just take the volume and multiply it by the molarity to get the number of moles. So I've added it in there. But as I'm adding the acid, what is it doing? It's reacting with the pyridine. And when it's reacting in a 1-to-1 ratio, we subtract out 1 times 10 to the negative third. But this is where you ask yourself, well, which one's the limiting reactant? Is it the acid or the pyridine? This one has fewer moles than the pyridine, so this is the limiting reactant, and we've learned since first semester general chemistry, the limiting reactant gets completely what? Consumed. And so that's why we end with no more acid at this point of the titration. And we end up with some of the pyridine left over. Now, as the pyridine is being consumed, what is being created? It's conjugate acid. Good. So we add 1 times 10 to the negative third moles here, and that's what we have after the addition. So first letter of A is what you've added here. This is actually what's added, but how does it affect, the other key ingredients in our equation? And the second letter of A stands for what's left over after the addition, after the reaction has taken place. Now is when you ask yourself, well, what's in my beaker at this point? And what's in my beaker is pyridine and its conjugate acid. So we can say weak base and its conjugate acid, which are the key ingredients of what type of solution? Of a buffer solution. Good. And the reason why I want to, emphasize this here is because you can have a shortcut. You can do a rice table here if you want to, but a shortcut, if you know you have a buffer solution and X is small enough to ignore, and it is in my second semester general chemistry course here, you can assume that's safe with these titrations, then in that instance you can use the Henderson-Hasselbalch equation. pH is equal to the pKa plus the log of the conjugate base, which in this case is pyridine, over the acid. It's conjugate acid. It's really important that we recognize when it's safe to use the Henderson-Hasselbalch. So we have a buffered solution at this point in the titration, so that's why it's safe to do that. Now we need to figure out the pKa. Well, the pKa comes from the Ka, so I'll write this up top here. We have the Kb already. We know Kw is equal to Ka times Kb. Kw is 1 times 10 to the negative 14th at 25 degrees Celsius. So if you have one, like if you have Kb, then you can solve for Ka. Like I said, we have Kb down here. So the Ka is equal to 5.882 times 10 to the negative 6, and the pKa is the negative log of that, which is 5.23. So that's going to be handy for the future questions that we're going to work as well. What's also really nice about Henderson-Hasselbalch is that since this is a ratio, you don't necessarily need to calculate the new concentrations. What I'm saying here is you don't need to divide by the total volume, because both of them would have the same total volume, and that essentially cancels out when it's a ratio. So it is also safe to use moles for Henderson-Hasselbalch and save yourself that step. So we're equal to 5.23 plus the log of 2.125 times 10 to the negative third over 1 times 10 to the negative third. And when you plug that in, you should get 5.56 for the pH. And you ask yourself, well, does this make sense? It should, because we're seeing that the pH is getting more acidic, and we have indeed added a strong acid to the solution. So it is as expected. Now, what is the pH after adding 20 milliliters? So let's go ahead and do that. So if you're adding the acid in, you're running a reaction, what type of table should you do first? You should do a BA table. So once you've derived the equation for that BA table, you're going to use it again. So same reaction is taking place, we're just adding more acid. So we've added 20 milliliters of HCl. Before addition, we had we put in 3.125 times 10 to the negative third moles. Remember, only work in moles. When we added 20 milliliters of a 0.1 molar solution of HCl, we added 2 times 10 to the negative third moles. But by adding it, it's reacting, so we have to subtract that from our base, our pyridine, because it's reacting 1-to-1 ratio. And at the same time as it's reacting, it's producing the conjugate acid. So that's why during the addition step, I like to see how things are changing and what's being produced. And in the end, what is left over? Well, you first have to determine your limiting reactant. Looks like the acid's still fewer moles than the pyridine, and so this is my limiting reactant, which gets completely consumed. So that's why it's 0 after the addition. We've created the conjugate acid, so that's there in this number of moles. And then the pyridine, we are left with 1.125 times 10 to the negative third moles. Once again, at this point in time, what's in my beaker? It is the weak base and its conjugate acid, which essentially is your what? Your buffer. Which means you can use what equation? Henderson-Hasselbalch. Okay. It's pKa plus the log of the base over the acid. So 5.23 plus the log of 1.125 times 10 to the negative third moles over 2 times 10 to the negative third, and you should get 4.98 for this one here. Once again, you can work with moles for Henderson-Hasselbalch because it's a ratio, so no need to calculate the final concentrations at this point. All right, part D is asking about the equivalence point. Now it's important that you remember the definition for the equivalence point. That's when the moles of what's in your beaker is equal to the moles of what's in your burette. So that's when the moles of the pyridine is equal to the moles of the acid that I've added, the hydrochloric acid. And so we know that we have added in 3.125 times 10 to the negative third moles of pyridine, which is the same as the acid. For every 1 mole of hydronium ions, I have 1 mole of pyridine. And then if I wanted to figure out, well, what's the volume I need to reach the equivalence point, then I can use the concentration, because I know what concentration of HCl I have in my burette. So in this case here, we would multiply that or divide it by the molarity. So we have 3.125 times 10 to the negative third moles of the hydronium ion, which is also the HCl. And we're using a 0.1 molar solution. And so we have 0.03125 liters, and that is equal to 31.25 milliliters when you multiply it by 1,000. So that's going to be important for us to know, well, how much do we need to add for my burette? We need to add 31.25 milliliters of the hydrochloric acid, which is our source of hydronium ions, to reach the equivalence point. Now, what is the actual pH at the equivalence point? So let's go ahead. When you do that, addition, you have to do the BA table. And so we have the pyridine plus the acid, just writing down the reaction again. Notice how when we write down the before addition, we always start with the same number. We start it with 3.125 times 10 to the negative 30. Do that for each of the steps. So hopefully you're starting to see a pattern here. Now, we needed to reach the equivalence point. We needed to add the same number of moles of the acid, so it would neutralize all of the weak base that was in my beaker. So when they react with each other, there's no limiting reactant here. They react 1 to 1, so therefore we're left with nothing for the pyridine and the acid. But what have we created in doing so when we're doing this reaction? You've created the conjugate acid. Good. So at this point, you ask yourself, what's in my beaker? What's in my beaker is the weak acid. And that's it. So we cannot do Henderson-Hasselbalch here because it's not a buffer system. There's no conjugate base. There's no weak base in our beaker at this point in the titration. There's only a weak acid, and to find the pH of a weak acid, just like what you did in chapter 16, you use the what kind of table? Rice. Good. So that's the critical step, is asking yourself, what's in my beaker at this step? All right. So when you do work with the rice table, it is important for you to find the new concentration. And so to do that, you need to find the total volume. So it looks like we added 31.25 milliliters of HCl, and we originally started with 25 milliliters of the pyridine solution. So our total volume at this point is 56.25 milliliters. And so our new concentration of our conjugate acid would be 3.125 times 10 to the negative third moles over 0.05625 liters. And so you should get 5.55, repeating fives, times 10 to the negative second molar. That's what we're going to use to put into our rice table for our initial concentration. So I'll move on to the next page for that. So just any normal weak acid, the acid donates the proton, the conjugate base of that acid is pyridine, and therefore water is acting as a base. It's a proton acceptor. The conjugate acid of water is the hydronium ion. Okay. So when we look at this here, initially we just calculated that at this point we have 5.5555 times 10 to the negative second of the conjugate acid after the hydrochloric acids reacted with the pyridine, and none of the pyridine and the hydronium ion in solution to a significant amount. And then we just do normal rice table. And we set that up to what? To the Ka value. So the Ka expression would be products over reactants, so x squared over 5.5555 times 10 to the negative second minus x is equal to 5.882 times 10 to the negative 6. X, assume, is small enough to ignore, and when you solve for x, you get 5.7141 times 10 to the negative fourth molar. Ask yourself, well, what does x mean in this part here? And this x is the hydronium ion. So we're dealing with a weak acid equilibria. And so if that's the hydronium ion concentration, we take the negative log of that number, And we get the pH is equal to 3.24. At the equivalence point. Now, what is the pH? I think part E was at 1/2 the equivalence point. Well, a handy kind of tip to remember is that at 1/2 the equivalence point, the pH is equal to the pKa. So that's just a quick trick to remember. We get that from the Henderson-Hasselbalch equation. pH is equal to pKa plus the log of the conjugate base over the acid. And at 1/2 the equivalence point, the concentration of the conjugate base and its weak acid are equal. And so if that's the case, you have 1/1 basically here. And the log of 1 is what? 0. So you can always derive it if you forget. But the pH is equal to the pKa at 1/2 the equivalence point. So you don't have to do, it can save you so much time from having to do any kind of calculations there. So in that case here, the pH is equal to 5.23, that pKa that we calculated earlier. All right. What about if we add 40 milliliters of HCl? What would the pH then be at that point in the titration? Once again, you're adding that HCl, that strong acid, that source of hydronium ions. We need to do a Baugh table. So we have the hydronium ion plus pyridine to give you the conjugate acid of pyridine and the conjugate base of the hydronium ion, which is water. We started off with 3.125 times 10 to the negative third moles of pyridine in our beaker before we added anything. And now we're adding 40 milliliters of a 0.1 molar hydrochloric acid solution. So we're adding in 4 times 10 to the negative third moles of these hydronium ions. Now you ask yourself, which one is the excess reactant? And which one's the limiting reactant? The limiting reactant now is pyridine, right? And so it will be completely consumed by the hydronium ions, which is your excess reactant. So when we subtract here, we can only subtract what is going to be consumed. So we can only consume 3.125 times 10 to the negative third to give us no more pyridine. It's been completely neutralized. And to figure out how much is left over after reaction, we need to take what we put in of the hydronium ions and subtract how much is reacted. So 4 times 10 to the negative third minus 3.125 times 10 to the negative third tells you how much is in excess. 8.75 times 10 to the negative fourth moles. So if you remember from first semester general chemistry, when you were asked to calculate the excess reactant, and I had you, if you are taking my class, I had you practice that again at the beginning of this semester. That's where this is coming into play. You're basically calculating, well, what is left over here? That's the excess. But remember, as we are reacting, we're creating the conjugate acid, and you can only make as much as the limiting reactant. Remember, the limiting reactant produces the maximum amount of product here that it can. Once we run out of it, we can't make any more, right? So at this point in time, we ask ourselves, what's in my beaker? And I have those hydronium ions, which is the strong acid, and that comes from the hydrochloric acid, and I have the conjugate acid of pyridine, which is a weak acid. Now, back in chapter 16, if you're taking my class, we discussed how do you calculate the pH of a solution that has a mixture of acids. Well, we learned that the pH is dominated by the strong acid, right? Because that strong acid will suppress the equilibrium of the weak acid due to Le Chatelier's principle. So all you have to do now is calculate the pH of a strong acid solution. You don't have to worry about doing a rice table here, because the weak acid will not contribute too much to the pH of the solution. And so what we need to do, though, in order to find the pH, we know it's the negative log of the hydronium ion concentration. Well, we need to figure out, well, what is the new hydronium ion concentration? So we have to calculate the total volume at this point in the titration, which is the 25 milliliters of the pyridine plus the 40 milliliters that we've added. This is 65 milliliters total. And so when we calculate the hydronium ion concentration, we're going to take 8.75 times 10 to the negative fourth moles, that's in excess, and divide by the total volume. That's critical. You divide by the total volume, and you would get a concentration of 0.01346 molar. And if you did the negative log of that, you should get 1.87 for your pH. Okay, so keep adding more acids, getting really acidic here. We have excess strong acid. This number makes sense. All right, and the final one is to calculate the pH after you've added 50 milliliters. And so following the same principle here, we have the hydronium ion and pyridine C5H5N. Let's see here. Conjugate acid and then water. Doing our BOD table, we started off with 3.125 times 10 to the negative third moles, and not including water here, we're adding in 50 milliliters of a 0.1 molar solution, so we're adding in 5 times 10 to the negative third moles. But remember, that pyridine is only going to react to the extent it's the limiting reactant. It's completely neutralized after 3.125 times 10 to the negative third moles have reacted. So to find the excess, we would take 5 times 10 to the negative third moles and subtract 3.125 times 10 to the negative third, and you would end up with 1.875 times 10 to the negative third moles of that strong acid in solution after the addition. We are creating the weak acid at the same time, so I just want to show that for completion. But we know that when we look at what's in my beaker, we have a strong acid and a weak acid. Which one wins? It is the strong acid. But before we can calculate the pH of the strong acid solution, we need to take into account the total volume. And so we have 25 milliliters of the pyridine that was added at the beginning initially, and then 50 milliliters of the HCl that's added. And so you have a total volume of 75 milliliters. And so to calculate the concentration after this titration at this point in time, you would take 1.875 times 10 to the negative third moles and divide it by 0.075 liters. And you would get the concentration. Let's see real quick. And divide it by 0.075, you should get 0.025 molar. And then to find the pH, you would take the negative log of that and you would get 1.60. All right, so to calculate or to draw the titration curve, you would need to put the pH on the y-axis, and then the volume of HCl added on the x-axis. And so Just drawing in the pH scale. And then we did 10, 20, 30, 40, and 50 mils added. So initially, our pH was 9.16 before we added anything, so weak-based solution. And then after 10 mils, it went to 5.56. And then at half the equivalence point, it's about 15.6 milliliters. That's half the volume to the equivalence point. We get a pH of 5.23. And then at 20 milliliters, we get 4.98. And at the equivalence point, which is about 31.25 milliliters, we get a pH of 3.24. And then at 40 milliliters, we drop down to 1.87. And then at 50 milliliters, we got 1.6. And so your titration curve would look something like this. So whenever you're dealing with a weak base titration curve, it looks like a backwards S, whereas when you're dealing with the weak acid, it looks like an S. So that's why it looks a little bit different than maybe what you saw on my online lectures. So make sure that when you're doing these problems that you understand every step of the way, like why you did a Baugh table, or why you did a Rice table, or why you use Henderson-Hasselbalch. Also, it's important that you visualize what's in your beaker and what's in your burette, so that you can successfully determine the reactions that are taking place. And remember to use those definitions: Bronsted acid, Bronsted base, what's a proton donor, what's a proton acceptor. So you're taking all that knowledge you learned from chapter 16 and applying it to a real-world application of titration. If you have any questions, don't hesitate to email me and let me know. I hope you found this video useful, and we'll talk soon.